Hi, so we're ready to look at section 3.2, which looks at measures of dispersion. So we have 5 objectives in this section. 1, we want to be able to determine the range of a variable from raw data. 2, we want to be able to determine the standard deviation of a variable from raw data. 3, we want to determine the variance of a variable from raw data. And 4, use the empirical rule to describe data that are bell-shaped. Right? Now, number 5, use Chebyshev's inequality describing a data set. We're going to omit that from the course, right? So this is omitted, right? So the very first thing we want to look at is what dispersion is, right? Because that's the focus of this section. So dispersion is the degree to which data are spread out, right? So what we want to look here is like how spread out are data. If you read this paragraph, it says to order food at a McDonald's restaurant, one must choose from multiple lines, while at a Wendy's restaurant, one enters a single line. The following data represents the wait time in minutes in line for a simple random sample of 30 customers at each restaurant during the lunch hour. This data is available in StatCrunch. So I also have this available in Canvas. Right, so if you go to the modules and datasets module, you'll be able to find this file there. Right? So I've already pasted the contents of that file into StatCrunch. So we'll be able to use that in this section. So you can see we have some questions, what's the mean, and also histograms and so forth. So let's first calculate the mean wait time, right? So I'm going to let StatCrunch do that for me. So I'll go to summary stats columns, and we want the wait time variable to get a summary of that. And I'm going to group this by restaurant, right? And we're looking for the mean, right? And if you wanted, we could also get the sum statistic and the end statistic, right? Hit compute, right? And also something else just to keep in mind, if you notice, if you look at the data, so each row, is a wait time. So I have the wait time in minutes, and then I have another variable restaurant that indicates if it's from Wendy's or McDonald's, right? So that's why I wanted to group it by restaurant, so that way I can get the mean time for McDonald's and the mean time for Wendy's separate, right? So you can see here in the table we have 30 cases for each, like was said, and then here are the sums, and then of course if I take the sum divided by n, that gives me the means, right? So I have the mean McDonald wait time is 1.389 minutes, and Wendy's is 1.391 roughly, right? So we can write that in here, right? And these are for a sample, right? These are a random sample of 30 customers. So we would use X bar in this case, right? So X bar, and I'll use subscript McDonald's to mean the sample mean for McDonald's. That was approximately 1.389, and that would be in minutes. Because remember, when you take the mean of a variable, the units are going to be the same as what your original variable is in, right? So our original data is in minutes. If I take the mean of a data set with minutes, I get minutes back, right? And then the X bar of Wendy's, right, the sample mean for Wendy's was 1.391 minutes, right? And you can see that these are about the same, right? They're approximately equal to each other, right? They're roughly the same value. Right? So now what we want to do is look at a histogram for each, right? So again, if I go back into StatCrunch, I can go to graph, histogram, I want to do wait time minutes, and here I want to break it up by restaurant again, right? And I'll go ahead and hit compute. So here is the histogram for McDonald's, right? So I could copy this. So I'm going to copy this image, and I can paste this into my notes, and then I'm going to grab the other one. Right, so close this, and I can just click over to the right arrow to get the other restaurant. So I'm going to copy this one, and I can paste that in my notes also. Right, so if we're looking at these, comparing these side by side, let me see if I can get these to be more in line with one another. There, it's a little better. Right, so when we're looking at both of these, right, so the one on the right is Wendy's, the one on the left is McDonald's. One thing, that sticks out to you about the shape is notice that the McDonald's is more spread out, the times, compared to Wendy's, where the bulk of the times are more closer together, right? So this is what we call like horizontal spread, right? Horizontal spread, right? How spread out your data is horizontally, right? So this goes, and also notice the scales are different, right? So this goes up to 5, where this only goes up to 4, right? But a bulk of my data is closer together here, where here it's a lot more spread out, right? With McDonald's. Also, a comment is that the picture of McDonald's, this is more right skew, right? Where the Wendy's is, this looks to be more bell shaped, right? Right, so see histograms from StatCrunch. Right, so they're over there. So next you want to be thinking about, which wait time appears more dispersed, right? So again, looking at those histograms, right? The McDonald's appears to be more dispersed, right? So this guy is more dispersed, right? It's more spread out, right? So there's more horizontal spread. And then the next question is, which line would you prefer to wait in and why, right? So I would say, waiting in the Wendy's line would be more ideal, because the wait time's more consistent, right? We have less horizontal spread, and we have a lot bulk of the data like in the center, where most people are waiting about the same amount of time, where the McDonald's seems to vary a lot more, right? So like all these bars have a fairly high frequency, right? And there's a lot more spread horizontally, right? So this seems to vary a lot more. You might wait 5 minutes, or you might wait 0 minutes, right? Where in Wendy's you're waiting, right around 2 minutes, like 1.5, 2 minutes, like pretty consistently, right? Right, so I would say, so McDonald's is more dispersed, right? So this one is McDonald's, and I would rather wait in Wendy's line because there's less horizontal spread. And the wait time is more consistent. Right? So that was just to get us thinking a little bit about dispersion, right? So we're thinking about how data is spread out. So the most simplest measure of dispersion is called range, right? So this is the most simplest. Oops. Most simplest measure of dispersion. Right. So we're going to use capital R to mean range, and the equation is just going to be your range is equal to your max minus your min, right? Your largest data value minus your smallest data value. So we're just looking for that difference. Right, so this next example is a data set we've been working with in the last section. So we have, these are the travel times in minutes to work for all 7 employees of a startup web development company. So we're asked to find the range, right? So first we want to identify what's the max and what's the min. Right, so the max here is 43 and the minimum is 5. So the range is going to be equal to 43, which, let me write this out. Right, the range equals the max minus the min, which equals 43 minus 5, which equals 38. Right, and this would also be in the same unit of minutes. Right, so we get the same unit back when we just subtract two things that have the same units. Right. So what I'd like to do now is I have this data set I already typed into StatCrunch. So if I go to stat and then summary stats and then columns, we can pick the variable that we're looking for. And notice what I needed here is I wanted the range, max and min, right? So I'll do max, min, and then range. I'll hit compute. Right, so here it's just identifying there's my biggest value 43, my smallest value is 5, and the range is the difference between those two, right? So if I take 43 minus 5, I get the range, right? So we can pick that up in the summary stats menu. Right, so that's how you could do that in StatCrunch, like if you had a large data set. All right, so then number 2 is we want to determine the standard deviation of a variable from raw data, right? So we're going to look at population standard deviation and also sample standard deviation. So unlike sample mean and population mean, those equations were pretty identical, right? So remember to calculate population mean, we use mu for population mean, right? And that was equal to the sum of the x of i's divided by capital N, right? So so then the sample mean, remember we use x bar to denote that, and that's equal to the sum of the x sub i's, but we divide by little n, right? Because little n tells me the count for the sample, right? So some things you want to remember is that this number here is called a parameter, where this number here is called a statistic, right? So statistic is a measurement of a sample, parameter is a measurement of a population. Right, so when we look at the population standard deviation, what this is looking for is the spread that's happening in the data, right? So this is the equation for population standard deviation, and we represent this symbolically with lowercase Greek sigma, right? So this like O looking thing is sigma, right? So something you want to know is that, you know, sigma is equal to the square root of the sum of the x sub i's minus the means divided by capital N. Right, so this is an equation you should know, right? And that Greek letter sigma still means sum, right? So we want to take all of the individual data values, subtract it from the mean, and then we're going to square them, and then we're going to add all those up, right? That's what that top thing means. So I think it's probably easiest to understand and be familiar with this equation if we do an example, and I like to do my example using a table, right? So the next is an example where we have the numbers 23, 36, 23, 18, 5, 26, and 43. And this is again that 7 employees start a web development company, and we want to calculate the population standard deviation. Right? So I'm going to go off to the side and work through this. Right, so this is an example of calculating population standard deviation by hand. Right, so my data is 23, 36, 23, 18, 5, 26, 43. Right, so the first thing I like to do is just count how many things we have, right? We have 1, 2, 3, 4, 5, 6, 7. So that tells me that capital N is equal to 7, right? Because this is a population. So then I'll just write down my equation for population standard deviation. So that's sigma equals the square root of the sum of x sub I minus mu squared divided by capital N, right? And if you forget, you know, how to calculate the population mean, mu is equal to the sum of the x sub i's divided by capital N. Right, so those are some equations we're going to need. So the very first thing that I would do is calculate the mean, right? So calculate the mean, which is mu. Right? So, you know, we did this in the last section, so mu is equal to the sum of the x sub i's divided by capital N, right? So in this case we have 7 things, right? So that would be x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 plus x sub 5 plus x sub 6 plus x sub 7, all divided by capital N, right? So writing that out long form. Remember that sigma notation just makes it a lot simpler to write. So remember also that this is x sub 1, this is x sub 2, so we're just like naming our data with these subscripts, right, for the first piece and all the way through the last piece, right, the seventh piece. So then this would be equal to, so just filling this in, we would have 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43, all divided by 7, which this is equal to, so the sum of those is 174 and then divided by 7, and this is approximately equal to 24.85714. Right, so you can see if I take 174 divided by 7, right, that's what I get in my calculator. So I wrote down 85714. So I rounded to what, 5 decimal places, right? So you can go as accurate as you would like. I recommend when you're doing standard deviation by hand to go out to at least 4 decimal places with the mean, so that'll help you be more accurate. Right, so that's the very first step. So then the next step that you want to do is to build the table. Right? So what you want in the table is you're going to want x sub I as a column. And then you're going to want x sub I minus mu. And then x sub I minus mu quantity squared. Right, so those are going to be like your three columns. So then now what you're going to do is just go through and list all of your data values under x sub I, right? So I have the numbers 23, and then 36, and then 23 again, and then 18, and then 5, and then 26, and then 43. All right, so now what we're going to do is just take each data value and subtract it from the mean, right? So I can just fill in my data values here, the x sub i's, and then you're going to do minus the mean. So the mean we found to be 24.85714. Right, so you just write that down all through. And then you could use your calculator and just subtract these. So the very first one, you should get negative 1.85714. And then if you square that, right, so here you're just going to take whatever value's here and square it. and we get 3.4489698. Right? So the next one, you take 36 minus 24.85714, and I get 11.14286. Right? So then for the next column, you're going to take that value, 11.14286. We're going to square it, and you should get 124.163329. Right? And then the 23, so we already did that here in this column, right? So we can just copy down those numbers. Then the next one is 18 minus the mean, so 18 minus 24.85714, so you should get negative 6.85714, and then we're going to square that, negative 6.85714 squared. That gives me 47.020368898. Right? And just a word of caution where some people make a lot of mistakes is that all the numbers in this column, the answer should be positive, right? Because we're taking a number squared, right? So they should always be positive. So be careful when you're working through this, right? Because you should know that like negative 5 squared is not equal to negative 5 in parentheses squared, right? And the reason being it's about the base, right? So when you see negative 5 without parentheses being squared, that's the same. So negative 5 squared is equal to negative 1 times 5 squared, which is equal to negative 1 times 5, which is equal to negative 25, right? Where if we focus in on this right side, when I have negative 5 squared, the quantity negative 5 squared, that's equal to negative 5 times negative 5, which is positive 25, right? So those are different things. So make sure you're using your parentheses and things correctly when you're squaring. Right? So then the next one, we have 5 minus 24.85714. So that gives you negative 19.85714. So when I square that, I get 394.306009. And then so we have 2 left, right? So this next one, the difference is 1.14286. And then squaring that, you get 1.30612898. And then lastly, 43 minus 24.85714. You subtract those, you get 18.14286. And then if you square that, you get 329.163,369. Right? So then the next part to do, now that we built that table, the third thing that we want to do is to find sigma, the sum of the x sub i's minus the mean squared, right? So that is going to be the number that goes here, right? So essentially you're just going to total this last column, right? That's what that means. Add up all of the x sub i's minus mu quantity squared. So we're going to add this number plus this number plus this number plus this one plus that plus that plus that. Add all those up, find the sum, and what you should get is 902.8571429, right? So in other words, sigma x sub I minus mu quantity squared is equal to this 902 number. Right, so then the very last thing you're going to do is just plug your items into the equation. Right, so remember we have sigma equals the square root of sigma x sub I minus mu quantity squared, all divided by capital N. So in other words, we kind of have two pieces here, right? We have this piece and we have this piece. So we just need to plug in those two things, right? So this is going to be equal to the square root of, so that top thing we found up here, that's 902.8571429, and n we already found to be 7, right? Capital N. Right? So you could take your calculator and take 902.8571429 divided by 7 and get that number, and then take whoops, that's not big enough, right? The 902 didn't go in. Let me try that again. So we took 902.8571429 and divide that by 7, and then we're going to take the square root of that number. Right, so I'm just going to take the square root of the answer, hit enter, and we get 11.3569 roughly, right? So that is the population standard deviation, right? So this would equal, approximately be equal to 11.357, right? And this would also be in minutes. So when you take the standard deviation of a data set, your units are still going to be the same, right? Right, so this is on the side. So on the top of the next page, this is the table typed out, right? So this did the same work that we just did. The only difference is the book likes to add in a column for the mean, which is perfectly fine. So then this column, you take the data value minus the mean, right, and get this number. And then this column is taking, whatever was over here and squaring it, right, just like we did. And then you need to find the sum of the last column, right? That's what this number is. And then you just plug these values into the equation, and we get an answer, right? So that's the population standard deviation. So essentially what standard deviation is like the average distance from the mean for the data values, right? So it gives you an idea for how spread out things are. Right, so then the next equation to look at is for a sample. So when we look for a sample standard deviation, we use the variable s to denote that, and the equation looks very similar, right? So one key difference is you're going to take the data values minus the sample mean instead of the population mean, right? So we're going to use x bar there, and then also this denominator is n minus 1 instead of capital N. So that n minus 1 is something we call degrees of freedom, and essentially all you really need to know is that it helps the equation be more accurate, right? Because if you put n in here, it doesn't get as close to what it should be. But if you do n minus 1, it seems to work out, right? So if you take more statistics classes, you might learn more about degrees of freedom, but that's what we call that. Right, so then I have an example of that. So this is a sample from those travel times of 3 things, and I want to walk through how to find the sample standard deviation. Right, so it's going to look fairly similar. Right, so first I'll just write down my sample. My sample is 5, 26, and 36. Right, so if I count what I have n equals 3, right? I have 3 things in my data set. I know that the sample mean x bar is equal to the sum of the x sub i's divided by little n, and I know the sample standard deviation is s, which is equal to the square root of the sum, right, sigma, of the x sub i's minus the sample means, quantity squared, divided by n minus 1, right? So those are the pieces of information I need. Right, so the very first thing you're going to do is to calculate the sample mean, x bar. So x bar is equal to sigma x sub I divided by little n, which would be equal to, if I let this be x sub 1, x sub 2, x sub 3, right, that would be x sub 1 plus x sub 2 plus x sub 3 divided by 3, which would be equal to 5 plus 26 plus 36 divided by 3, which that sum at the top should be, 67 divided by 3, which that's approximately 22 point, and then it's really an infinite number of 3's, but I'm just going to round to 4 decimal spots. Right, so we get 22.3333. Right, so we calculate the mean first, just like before. The next step will be to complete the table. Right, so the table will look a little different, but not much. Right, we'll have a column for each data value. Right, so we have 5, 26, and 36. And then we need a column to take x sub I minus the sample mean. And then the next column will be to square those. Right? And then down here, right, we can make like a box here where this is the sigma of x sub i's minus the mean, sample mean squared. That's going to equal the value in that box, right? So, first we would take, 5 minus 22.3333, which gives me negative 17.3333. If I square that, I get 300.4432.889. Right? So the next one, I would take 26 minus 22.3333, which gives me 3.6667. And then I'm going to square that and get 13.4446.8889. And then lastly, I'm going to take 36 minus 22.3333, which gets me to 13.6667. I square that and get 186.7786.889. And then I total these numbers up, right? So add these 3 numbers together, and we get 500 point, and then 6 sixes, and then a 7. Right? So really this last part, the third step, is to find the sum of the x sub i's minus x mean x bar squared. Right? That's what we did here. So then now the very last thing is just to plug into your equation. Right? So my equation is x equals the square root of sigma x sub I minus x bar quantity squared divided by n minus 1. So this would be the square root of, so this top numerator, right, is just that number, which is 500 point, and then 6 sixes, and then a 7. And then you're going to divide by n minus 1, which n minus 1, n is equal to 3, right, remember? So this would be 3 minus 1. Right? So we can just grab calculator. Right, and I can take 500 point, and then 1, 2, 3, 4, 5, 6 sixes, and a 7, and then divide that by 2, right? So 3 minus 1 is 2. And then I need to take the square root of that answer, and I get 15.8219 roughly. Right, so this is approximately equal to 15.82, and this would still be in minutes. Right, so in other words, like the average distance from the mean for those three numbers for that sample was 15.82 minutes, right? Where the average distance from the mean for the top problem, right, where we find out the population. Let me find where that number was. Right, was 11.357 minutes, right? So the average distance from the mean for each of the data values is 11.357. So this number again tells us how spread out things are, right? All right, so we calculated this, right? And we got what roughly S was approximately 15.822 minutes. Right, and that's off to the side. Right, so if you scroll down at the top page, so this is another filled-in table, like how the textbook would do it. Same idea, but I think it's helpful for me to go through the table with you rather than just show you the table, right? So that's why I was doing that off to the side. Right? So then the next example is comparing standard deviations. So it says determine the standard deviation wait time for Wendy's and McDonald's, which is larger, and why. Right? So you could imagine, we could do this by hand, but we have 30 sets of data for each thing, so that's pretty time consuming, right? So I would definitely use StatCrunch to help with that. Right? So what I can do is go to stat, summary stats, and then columns, and we'll look at the wait time variable. I want to group by the restaurant, and what I'm interested in is the standard deviation, right? So if I hit compute, I'll get this number. So you can see the standard deviation for McDonald's is 1.26 roughly, where Wendy's is 0.73. So you can see that the standard deviation is higher for McDonald's, so that corresponds with having more horizontal spread, right? There's more variation in McDonald's versus the Wendy's. So Wendy's data is closer together, where McDonald's is more spread out, right? Just like how we were looking at the beginning, like at the histograms. Right, so we can fill this out, right? So these are for samples, so I would use S, right? So the S sub Wendy's was equal to 0.738, we'll say, and this would be in minutes. And then S sub McDonald's was equal to 1.265 5 minutes, right? So it says which one's larger, right? So the McDonald's is larger, right? So S sub McDonald's is larger because the wait time for McDonald's has more dispersion, so more spread out slash, more horizontal spread than Wendy's, right? The Wendy's times were closer together, right? So it can be somewhat hard to just look at some histograms or look at the raw data and know which one's more spread out. So that's why it's important to calculate standard deviation, right? So now that I have these numbers, it's a way to quantify that dispersion, right? So the higher the standard deviation, the more spread out your data is. If your standard deviation is closer to 0, so in other words, the smaller it is, that's going to give you, your data being closer together, right? If you have a standard deviation of 0, that means like all of your data is like the same number, right? There's no spread. Everything's the same, right? So then this next part here, it says the standard deviation may be used to judge whether a particular observation is far away from the mean of a data set. So it says, for example, is 31 centimeters far from a mean of 25 centimeters? If the standard deviation of the data set is 6 centimeters, then the answer is no, because 31 would only be 1 standard deviation from 25. However, if the standard deviation is 2 centimeters, then the answer is yes, because 31 would be 3 standard deviations from 25. Right? So let me come off to the side to look at this. Hang on, it's not wanting me to. There. Right. So let me go through this a little more so you can see. So we're looking, basically what we're looking at is if we have a mean of 25 centimeters, and we're looking at a couple of cases. One where the standard deviation is 6 centimeters, and the other case is where the standard deviation is, what was it? 2 centimeters. Right, and we're considering the value of 31. We're wondering, is that far away, right, from a mean of 25? So if I take 25 plus 6, that gets me to 31, right? So in other words, this was the mean plus 1 times a standard deviation, right, would equal to 31, right? Because 25 is the mean and 6 is 1 standard deviation. So we only have to go 1 standard deviation to get to that number. So that's not far away, right? Not far away. Where the next one, the standard deviation is 2 centimeters, so this is the average distance away. But here, I'm going to have to take 25, and I'm going to have to add 2 to it 3 times in order to get to 31, right? In other words, 25 plus 3 times 2 equals 31. And that's like taking the mean plus 3 times the standard deviation to get 31, right? So in other words, this is 3 standard deviations away. Right, where this one was just 1 standard deviation away. So, so this is far away. So this concept will make more sense after we look at the next learning objective, because we'll look at what's called the empirical rule. But the general rule of thumb is, if you're anywhere from 0 to 2 standard deviations away, this would be typical or not far away, right? But if you're more than 2 standard deviations away, then typically we say that this is, like atypical or far away, right, from the mean. So that's kind of the general rule of thumb, right? So, and you'll see why in a minute in the next rule, right? So just focus on that for right now. So then if you look, the next example, it says, example far away, it says, is 1,000 far away from 900? As someone with knowledge of measures of dispersion, your answer should be, it depends, right? It depends on the standard deviation. So we don't know if 1,000 is far away from 900 without knowing how spread out your data is normally, right? So part A says, let's say the standard deviation is 25, right? So in other words, here your mean is 900. Your standard deviation is 25, and we're considering the data value of 1,000. We want to know, is it far away, right? So here you would have to take 900 plus 4 times 25 to get to 1,000, right? Because we need to add in 4 standard deviations, right? 4 times 25 to get to the 100 that we need, right? So this would be like your mean plus 4 times standard deviations to get to 1,000. So this is far away, right? Because it's more than 2 standard deviations away, right? We had to add 4 of them, right? Where the part B is looking at the same thing, but now my standard deviation is 120, right? So we're still thinking the mean is 900, and I'm looking at the value of 1,000. I want to know, is that far away, right? So in this case, I would have to take 900 plus, plus 100 to equal 1,000. Well, something that's important to note is that this number is smaller than 120, right? So in other words, we're going to take the mean plus less than 1 times your standard deviation to get to 1,000. So this is less than 1 standard deviation away from the mean, right? The number 1,000. So this is not far away, right? So it all depends on what the standard deviation is. Right? So then the next part is looking at what variance is. So variance of a variable is the square of the standard deviation, right? So to calculate the population variance, you're just going to take sigma squared, and the sample variance is s squared, and we use those symbols to denote the variance, right? So we're asked to calculate the population and sample variance of this data. So I'm going to use that sample we used before, 5, 26, and 36, to calculate s squared, right? So if we look at, for the population, we found sigma to be 11.36 minutes, roughly. So sigma squared, which is the variance, would be equal to 11.36 squared, and the units would be minutes squared, right? So this gets me to 129.0496 minutes squared. Right, so notice the units are whatever units you started with squared. That makes it kind of awkward to talk about. So that's why, typically we don't look at variance all that much. We normally just look at standard deviation because of that, right? So that way it's in the same units as what your data is. It makes it feel a little more meaningful, right? where S from this population, or it's from this sample, right? This sample of three things, the sample standard deviation was 15.82 minutes. So S squared is equal to, that would be 15.82 squared minutes squared, right? So that gets you to 250.2724 minutes squared. Right, so notice the units is what your data was squared. Right? So not too hard, right? Once you can calculate standard deviation. All right, so then the next thing to talk about is called the empirical rule. So if a distribution is roughly bell-shaped, then the following is true, right? And for bell-shaped, remember that a bell shape is unimodal and symmetrical. Right? Unimodal means there's one mound, and symmetrical means that it's symmetric, right? So in other words, the bell-shaped curve looks like this, right? Where you got one mound and you have symmetry. Right? So this is bell-shaped. So approximately 68% of the data is going to lie within one standard deviation of the mean, right? And then approximately 95% of the data is going to lie within two standard deviations of the mean, and approximately 99.7% of the data is going to lie within three standard deviations of the mean, right? So these three things these three bullet points are something special that you're going to have to know. We're going to use a lot, right? And this applies if you use the sample mean or the population mean, right? It still works in both cases. And this is often referred to as the 68, 95, 99.7 rule. Right? So you definitely want to know these three numbers and know them well, because we're going to use it a lot. Right? So I usually joke with my students, you want to get a tattoo of this, right, or something. All right. So then the next part of this page is a diagram to help you understand what's going on, right? So, and it might be helpful if we build this together off to the right so you fully understand all the pieces, right? So I'm just going to go off to the right, right? So I'm going to make a line, make my bell curve, right? So the important thing you want to get from this is right down the center is going to be the mean, right? So this is mu, right? The mean. And then what we're told is if you're within one standard deviation of from the mean, that's where 68% of our data is going to lie, right? So if I go to the right, so plus one standard deviation, and I make a tick mark, and then I go to the left one standard deviation and make a tick mark. Then if I follow this up, right, then inside of here, right, so this shading is going to be 68% of my data, right, by the empirical rule. And then so the next thing is if I go two standard deviations, right, and also we can label this. So this tick mark, the value would be one mean plus standard deviation, right? Where this would be your mean minus a standard deviation. So then the next thing is if I go another standard deviation, right? So plus one more standard deviation, and then this way I go minus one more standard deviation, and I put a tick mark. Right? So this value would be mu minus 2 standard deviations, and this would be your mean mu plus 2 times sigma times 2 standard deviations. What we would expect inside of here, so all of this we would expect 95% of my data, right? And then lastly, right, we can go one more standard deviation, so plus one standard deviation, and then minus one more standard deviation this way, make a tick mark. So this tick mark value would be the mean minus 3 standard deviations, and this would be the mean plus 3 standard deviations. Then inside of here, so all of this, right, all of this, from here over, that would be 99.7% of the data. Right, all of that is 99.7%. Right, so that's what that table means. Right, so then, this table is a little different, or that picture, that diagram. Let me scroll over. So notice what it does is it splits up some of these pieces and labels them a little bit different percents, right? So I can talk about how that happens, right? So if you go the area all the way under, so the total area is equal to 1, right? All the way across, right? Another thing you want to know about this diagram is when you go to the right of the mean, that's 50%, and when you go to the left of the mean, that's also 50%, right? So in other words, the mean cuts it in half, right? So you're going to have 50% of the data to the left of the mean and 50% of the data to the right of the mean, right, when you have a bell curve. Right, so we have that labeled. And then, here to here is 68%. So if I have the mean right in the middle and half's on the left and half's on the right, if I take 68 divided by 2, that's where I get these 34 numbers, right? And then you might be wondering, how do you get these numbers here, right? So that would be, so I know from here to here is 95% of my data, and I know, here to here is 68%. How would I figure out these two parts, right? Well, the sum of those two parts would be 95 minus 68%, right? Because you would just take, see if I can label this a little better, right? So this part is 95%, and this part is 68%. So if what I'm after is trying to find just these parts here, this part and this part. So if I take the total area that I'm looking at, right from here to here, which is 95%, and I subtract off this middle piece, what that's going to leave me with is this area plus this area, right? So that gets me to, take my calculator and take what, 95 minus 68, right? We get 27, right? So then if I take that number now divide by 2, that gets me to 13.5, right? So that 13.5, so this was equal to 27. And then if I take 27% divided by 2, that gets me to 13.5%. And that's where these numbers are coming from, right? So if I erase that now, you can see that 13.5% is what's under each of these spots. Right, so then you could keep repeating that process to get the other pieces, right? So like to figure out this number, the 2.35, you would need to take 99.7 minus 95 and then divide that by 2, right? And then what's left on these tails, right, would be 100% minus 99.7 divided by 2, right? All right, so just to give you a little idea for how those are and where they came from. So then now something we could do is we could fill in the mean and so forth, right? So it says the waist circumference of a 2-year-old male is bell-shaped with a mean of 48.5 centimeters, right? So this would be 48.5 centimeters. And then the standard deviation is 4.8 centimeters, right? So the mean is 48.5, and the standard deviation is 4.8 centimeters. So it says about 95% of 2-year-old males will have waist circumference between what two values, right? So the 95% would be 2 standard deviations away, right? So both these two things, right? So in other words, what you're going to want to do, right, is take mu minus 2 times standard deviations, right? So that would be 48.5 centimeters minus 2 times 4.8 centimeters, which that comes out to be the following, right? So we need to take 48.5 minus 2 times what, 4.8. We get 38.9, and then we want to take that same thing and just put a plus instead of a minus, and we get 58.1. Right, so those are the two numbers that we're after. Right, so this was equal to what, 38.9, and then mu plus 2 times theta, 2 standard deviations. That was 48.5 plus 2 times 4.8. That gets me to, what was it, 58.1, and these would both be in centimeters, right? So you could fill in the values to this table if it's helpful, right, underneath. Right, so it turns out if you add 1 standard deviation, this number is 53.3, and then this number is a 58.1, and then this is 62.9, right? And then you can keep subtracting, 4.8 centimeters. So we have 48.5 in the center, so that would be 43.7, and then 38.9, and then 34.1. Right? So between these two values, we would expect 95% of the 2-year-old males. And then part B says, what percentage of 2-year-old males have a waist circumference between 34.1 and 62.9, right? So we're looking between 3 standard deviations, right? 34.1 and 62.9. So that would be the 99.7%. Right, because they're within 3 standard deviations. Right, so in other words, mu minus 3 times sigma gets me to the 34.1, and mu plus 3 times sigma gets me to the 62.9, right, value. Then lastly, it says, what percent of the 2-year-old males have a waist circumference between 53.3 centimeters and 62.9, right? So we're looking at these two areas here, right? So it turns out we can add those numbers together, right? So what you would do is take the 13.5% and add it to the 2.35%, and you get 15.85%. Right, so I just added these two numbers together, right, because we're looking at between these two values. Right, all right, so that's all I have for this section. Let me know if you have any questions. Thanks.